In this, the sixth lecture, after the brief overview of the course, we will now talk about the constituents of matter in terms of atoms, nuclei, and fundamental particles. So, of course, the atom has its characteristic X-rays and gives rise to the photoelectric effect through its interaction with photons. Then there is this question of radioactivity, which has led to the detection of alpha, beta, gamma radiation and spontaneous fission decay, and of course in more modern times even spontaneous proton decay, composite particle decay and so on. And then we will the other thing that happens is that nuclei are probed via electron and composite particle scattering as well. Now, just before I begin, let me also give a quote from Millikan's lecture. Millikan is famous for the oil drop experiment in which he found the quantum of electric charge of the electron in the famous experiment. And so in his Nobel speech in 1923, he, and I quote, he said the following: "Science walks forward on 2 feet, namely theory and experiment. Sometimes it is one foot that is put forward first and sometimes the other, but continuous progress is only made by the use of both, by theorizing and then testing, or finding new relations in the process of experimenting and then bringing the theoretical foot up and pushing it on beyond, and so on in unending alterations." So these are actually two arms of the same science, theory and experiment. So although my emphasis in this set of lectures is on experiment, but that doesn't mean that I will only talk about experiment, but also a little bit of theory. The world around us must have always fascinated human beings. As intelligent creatures who have been around for about a couple of million years, what the human being sees around, both on the land, sea, as well as in the skies, must have fascinated him. And among other things, must have wondered what are the underlying constituents and rules that govern their behavior as we advanced in our civilization. So observation and their careful study led to our present day understanding. And this understanding is that all the matter that we see around us consists of fundamental entities, atoms and molecules, and they interact primarily via electromagnetic interactions. When a large number of atoms and molecules come together, you get, of course, a solid or a liquid or a gas. Of course, there is a so-called fourth state of matter in which you have positive ions of atoms and electrons. And indeed, a lot of outer space does consist of these plasmas, as indeed most of the sun is in a state of plasma. There is now also a fifth state of matter that we have found, namely the Bose-Einstein condensate, where a large fraction of bosons, they could be atoms or molecules, they occupy the same ground state. This happens, of course, at extremely low temperatures, and this has been seen only because we have now techniques to cool down things to micro or nanokelvin temperatures. So, in a solid crystal, for instance, you have atoms, molecules, or even ions. So, for instance, sodium chloride crystal, you have sodium plus ion and chlorine minus ion. Then you have liquids, which have atoms, molecules, ions, but with spacings of the order of an angstrom unit, 10 to the minus 10 meters. It's similar as in solids. In a gas, on the other hand, you have the same entities, but with much larger spacing at NTP. Of course, if you compress the gas, the spacings come down. So, this is a cartoon which shows the atom on the scale of 10 to the minus 8 centimeters or 10 to the minus 10 meters. And then you have, it is composed of electrons and a compact nucleus. The nuclear dimension is of the order of 10 to the minus 12, 10 to the minus 13 centimeters, depending on how large the nucleus is. And then the nucleus itself consists of protons and neutrons, and the protons and neutrons themselves consists of, as we now know for the last 50, 60 years, they consist of quarks with even more compact dimensions. of the order less than, and there's supposed to be, as far as we know, point particles. Less the sizes, if they are indeed finite, are less than 10 to the minus 16 centimeters or so. So we have done this by looking at matter in smaller and smaller spatial resolutions. We have already briefly discussed the experiments of Perrin that showed that liquids consist of atoms or molecules. Rutherford showed that you have a compact nucleus at the center of an atom. Thomson, of course, was responsible for the discovery of electron. Then the discovery of X-rays, which are just photons of high frequency. This was shown by Rontgen. Radioactivity, of course, the seminal work of Becquerel, Marie and Pierre Curie, and of course later Rutherford, Soddy and so on. So the discovery of isotopes was done by Soddy, and mass measurements which led to the binding energy, famous binding energy curve in nuclei due to Aston. Wien showed that the canal or anode rays have the opposite charge as the cathode rays, which were used by Thomson to infer that electrons exist in atoms, and because they have a much larger charge, much larger m by e ratio, so much larger mass as compared to the charge. And Thomson, of course, measured the magnitude of this electric charge and showed that the E by m ratio is consistent with that of the positive ion of hydrogen. Rutherford in 1920 showed that the reaction of nitrogen plus alpha particle, using alphas from radioactive sources like radium and so on, it gave rise to particles that produce scintillations on a zinc sulfide screen. And the important thing that he found was that these particles have a much longer range than the alpha particles in air, for instance. Okay? So he concluded that these hydrogen nuclei were constituents of nitrogen nuclei. So as a result of this reaction, the proton came out of the nitrogen nucleus, and this is what he measured. Now we come to the quantum of electromagnetic radiation, the photon. James Maxwell unified electricity and magnetism, and this is summarized, of course, in the so-called Maxwell's equations. This is shown here. This is a plaque showing Maxwell's equations at the Edinburgh statue of Maxwell, James Maxwell. The key prediction of Maxwell's equations was the electromagnetic radiation that can be produced by accelerated electric charges, or indeed electromagnetic distributions in general. So you can even have a magnetic moment that is accelerated and you can produce electromagnetic radiation. So this is a key prediction. And indeed it turned out through other experiments of Hertz and so on that you can have radio emission, you can have visible photon emission and so on. That is of course done later. The other key thing that happened was that the wavelength distribution of radiation from a so-called black body could not be explained theoretically, especially at the short wavelengths and in combination with what is there in long wavelengths, you could not explain the whole spectrum simultaneously. So classical physics could not explain the so-called black body radiation spectrum. This is where Max Planck came in, and he showed that the whole spectrum can be explained if the energy exchange between electromagnetic field and atoms occurs via quanta. So he introduced the concept of the quantum of action, the Planck's constant. But before that, let me just show you a typical black body or typical black body spectra. So on the left you see a typical black body spectrum. So the radiation intensity as a function of wavelength, the wavelength here is in micrometers. So you can see that it rises and then falls, and the peak shifts to smaller wavelengths as you increase the temperature of the black body. Okay. This is the ultraviolet region and this is the infrared, and of course what is shown is the longer wavelength, which is red part of the spectrum, then the yellow, green, blue, and then the violet. This is again shown here in a blown up fashion, where the classical theory for a black body radiation at 5000 Kelvin, this is the classical theory. So, although it does probably reasonably well, this is the experimentally, let's say, measured spectrum, and it does well for the long wavelengths, but it doesn't at all explain the spectrum at smaller wavelengths. So, Planck derived a so-called Planck radiation formula, which basically says that the spectral density or the intensity as a function of frequency goes like frequency to the cubed divided with some constant, which involves the quantum of light, which is h, this is the so-called Planck's constant, and this denominator has the energy of the quantum, which is related of course to the frequency through the Planck's constant, divided by the Boltzmann constant times the temperature of the black body, and then of course this factor minus 1. This is the so-called Planck radiation formula. Of course, later, about 25 years later, this was also arrived at by S.N. Bose, who assumed that light quanta obey statistics known as the Bose-Einstein statistics. So, he had a much simpler way of deriving this same formula. Philip Lenard made an observation of photoemission when you shine electromagnetic radiation onto a surface, material surface, and he found that the energy of the emitted electron was actually proportional to the frequency of the incident electromagnetic radiation, but not, and this is important, not on the intensity. Classically, the energy should have been related to the intensity of the radiation at whatever frequency. Okay, so this was an observation that could not be understood within the classical theory, and Einstein, in one of those quartet of papers which he wrote down in 1905, he could explain the photoelectric effect using the concept of the Planck quantum, and he called it the photon. So, then the energy of the electron, the ejected electron, is just related to the energy of the photon through this h nu, energy of the photon, minus the so-called work function of the element on which this light shines, or this electromagnetic radiation shines. This work function of course depends on the material. If you shine it on an atom, then it depends on the binding energy of the electron in the atom or molecule, as the case may be. And if the energy is not sufficient to take out this electron from the materials, then of course you have zero, you do not get an electron. But if you increase the energy of the photon beyond the work function, then of course the energy of the electron keeps rising. And this is shown in the next slide, where a photon hits a solid, for example. It could also be an atom or a liquid, and then you have an ejected electron. Okay, the energy of the electron is related to the frequency of the photon, and there is a threshold frequency below which no electron is ejected. So, this is shown also graphically here. The energy of the ejected electron, it only starts, the process starts beyond a certain threshold frequency, after which it rises linearly. Okay. A confirmation of this idea of the photon was the observation of the scattering of X-rays by free or bound electrons by Compton in 1923. So, here a photon, or actually electromagnetic radiation, shines on the electron, and then electromagnetic radiation scatters off, and then the electron recoils, and the energy of the scattered photon is related to the energy of the incident photon through this relationship, if you consider electromagnetic radiation to be in the form of photons. Okay, so this is first of all non-isotropic, but also in a very specific, the energy of the scattered radiation or of the scattered photon, or the frequency of the scattered photon, the wavelength of the scattered photon is related in this through this relation in a very specific manner with respect to the scattering angle of the final photon, the scattered photon. Again, this is depicted here. You have a X-ray or gamma ray coming in, and then it scatters off at an angle. elastically on the electron, which recoils with an energy of E. So, of course, the sum energy of E gamma prime and EE is, of course, the energy of the photon that was there to start with, and theta is the scattering angle of the photon. There is another angle here, of course, which you might call phi, and of course, these are related to the energy momentum conservation principle. So, this is the experimental apparatus that Compton and his colleague used, and this is the report. This is reported in 1925 in Physical Review. So, you actually collimate these X-rays, which are in this particular experiment, it was done using a tungsten exploding wire, and you collimate it using this, this set of slits. Then you have lead all around so as to shield the rest of the apparatus from photons that are moving in all directions. So, this is the set of 3 collimators that, and also this one, which enables the angle, input angle to be defined, or input direction of the photon to be defined fairly precisely. It enters a cloud chamber, and then it interacts with electrons in the cloud chamber to produce a recoil electron and a scattered photon. Of course, the recoil electron is detected in the cloud chamber directly. You can see this is the track, and then you can extrapolate it to the vertex. And similarly, this vertex can be used to construct the direction of the photon, because the photon cannot directly be seen in the cloud chamber, but it interacts a bit later and you have a recoil electron. This is what is measured, and so if you extrapolate the starting point and then you join it to this vertex, then you get the scattering angle of the scattered photon. So, he did this for a large number of tracks, and exposed something like 1300, in which you also picturize, you take photos in 2 cameras so that you can get a stereo picture, and then ultimately he found that 18 have a reconstructed angle within 20 degrees of what is expected if you were to consider this as a photon scattering of an electron. So, this indeed was experimental demonstration that X-rays can be thought of as photons in this particular interaction, photon scattering of an electron, and this came to be later known as Compton scattering. So, in all this, these were the scientists involved. Of course, Max Planck, who is the father of the quantum, he got the Nobel Prize in 1918. So, all of these scientists won Nobel Prizes in various years. Philip Lenard won this for the experimentation with cathode rays and X-rays on targets and so on. So, he won the Nobel Prize in 1905. Then the photoelectric effect that he observed and couldn't be interpreted within the classical physics was interpreted by Albert Einstein, who got the Nobel Prize for that in 1921. Of course, it is interesting that his Nobel talk actually talks more about the special theory of relativity and very little about the photoelectric effect. Arthur Compton, of course, also got the Nobel Prize in 1927 for discovering the Compton effect and actually providing further evidence that light consists of photons. These are the key papers, Max Planck's paper in 1901, Lenard's paper in 1902, Einstein's paper in 1905. Of course, this is one of, as I said, among 4 seminal papers, and Compton's paper in 1925. So, in 1913, after the experiment of Rutherford, which showed that in 1911 that the nucleus exists at the center of the atom, he modeled the atom as being electrons moving around in quantized stationary orbits around a compact nucleus. And now, of course, if you have electrons orbiting a nucleus classically, then they would radiate and eventually they will fall back into the nucleus. The fact that a hydrogen atom lives forever, or as far as we know, means that there is something that prevents it, and Bohr actually made that into an assumption. He said that there are stationary orbits in which the electron can move forever, and there are different orbits, and so these different stationary orbits are such that you can have transitions between them. You can either excite them from a lower state to a higher state, or from a higher state you can de-excite, and that's how you can interact with the electromagnetic radiation. So you can either have emission or absorption of electromagnetic radiation. So indeed, he predicted the spectrum of the hydrogen atom, the various lines that you get, and this was a great confirmation of this. But of course, his theory went beyond just the hydrogen atom. This was something that the whole of the periodic table was actually a result of atoms which were with the structure which he helped build up. Moseley followed up this in 13 and 14 and showed that the characteristic X-ray energies depend on the atomic number of the element. So, for instance, K X-rays, where you create a vacancy in the K shell, the innermost shell, the 1s orbital, if there is a hole there, then the outer electron can make a transition there and you get a characteristic K X-ray. So, the energy of this characteristic X-ray of course depends on the atomic number of the element, and indeed that energy is proportional to Z squared. Marsden and Rutherford found a penetrating heavy charged particle in alpha plus air interactions. That is what I mentioned earlier, namely the proton. Since the mass of the nucleus did not match with the atomic number, then which is A, as opposed to Z, which is telling you the number of protons. So Rutherford theorized in 1920 that a certain number of electrons cancelled the charge of the excess proton. So at that time the neutron was not known. So it was believed that there are A protons and Z minus A electrons actually neutralize the excess charge, so that you have effectively a charge Z in the nucleus, so as to be consistent with the characteristic X-rays and Coulomb scattering. Rutherford actually did propose the existence of a neutron in 1920, but he did not pursue this idea for long. There are other things that were taking up his concern. Sometime in 31, 32, Bothe, Becker, Irene Curie and Joliot found a very penetrating radiation which they thought were very high energy gamma rays as being produced in alpha plus beryllium interactions. They found proton recoils of energy about 5 MeV when a very thin layer of paraffin was interposed, as you could measure in a cloud chamber or in a ionization chamber. This explanation had two problems. If this is very high energy gamma rays that are producing it, then the energy of that gamma ray has to be very high, 50 MeV. And where do you get this 50 MeV from? Not only that, the probability of the gamma P interaction also has to be much larger, in fact by the order of 1000 as compared to that predicted by the Klein-Nishina formula, which did very well in predicting the photon electron interaction probabilities, cross sections. So Chadwick in 1932 settled the issue using an ionization chamber and also cloud chamber pictures of proton recoils. Indeed, this definitive experiment also estimated the mass of the proton to be very close to that of the neutron, of this neutral particle, neutron, to be close to that of the proton. So after Chadwick's experiment, of course, it became clear that you don't need electrons in the nucleus. You have n protons and n neutrons and z protons, and they make up the mass number, which is A, which is equal to n plus z. I think I made a mistake, atomic number I said at some earlier time. It is actually mass number. Okay, so A is equal to n plus z, and this is the key reference which is given here. So just to show that this proton of kinetic energy 5 MeV cannot come from a Compton scattering of a high energy photon, you can quickly estimate what is the energy of the proton coming about from the recoil of a high energy photon, and this is the expression where c and mp are the speed of light and mass of the proton, and we can get the energy of the photon. You can estimate this as the square root of the energy of the proton times the mass of the proton, rest mass of the proton, and that comes out to be of the order of 50 MeV. And of course, using Aston's mass measurements, the energy of the gamma ray in this reaction is only of the order of 10 MeV. So, this is way too small as compared to 50 MeV. So, this cannot be a gamma ray. And of course, as I said, this puzzle was solved by Chadwick by assuming electrically neutral radiation is emitted in the above reaction, not a gamma ray. And this was called the neutron. So, the sequence of reactions is as follows. 9 beryllium interacts with alpha to produce carbon 12 plus the neutron, and then this neutron elastically scatters off the proton, let us say in the paraffin, and then this is detected. And of course, when it scatters, it can scatter at any angle. So, the maximum energy of the recoiling proton is of the energy of the neutron. The discovery of the neutron led to an understanding, of course, of isotopes of elements, which have the same Z but different N. The electrical neutrality of the atom, you have Z protons in the nucleus and you have Z electrons in the atom. The electrical neutrality of the neutron meant that it can very easily penetrate matter because it does not interact, it cannot ionize atoms or molecules. And of course, they can undergo neutron capture reaction through this strong electromagnetic interaction. So, in this case, this capture is the electromagnetic process. Chadwick, of course, it is interesting that Chadwick had suggested that this neutral particle, neutron, consists of a tightly bound proton and electron with a binding energy of a couple of MeV. Of course, this turned out to be wrong because as we know from future developments, let's say the uncertainty principle, that the electron has to have a very large energy if it has to reside close to the proton, and there is no fundamental interaction which can lead to that, and so this idea turned out to be wrong. So, the neutron, of course, because of its neutrality, electrical neutrality, can be used to transmute elements. It can get captured by nuclei and can make heavier nuclei, and this is a much easier and more efficient way of transmuting particles than charged particles, at least certainly in those days where the only source of charged particles was alpha particles from radioactive sources like radium and so on. Charged particle face the Coulomb barrier, and so you have a limited amount of reactions that you can do, whereas neutrons, being neutral, they can be captured by the lightest to the heaviest elements. So, Enrico Fermi indeed in Rome started this program of irradiation with slow neutrons in order to make new elements. This effectiveness, of course, was discovered by him accidentally by interposing, instead of lead, a paraffin block, and then he could explain that it increases the rate of production very simply because then it slows down the neutrons, and then these slow neutrons have a large cross section for interaction. Lise Meitner used this same neutron irradiation technique to start this program of producing transuranic elements, and in fact this led to the discovery of fission, which is a very important event in the history of science. The positron, by the way, was discovered by Carl Anderson. So, Dirac invented the equation which goes by his name, which combines quantum mechanics and special theory of relativity. So, this equation is consistent with the special theory of relativity, but also with quantum mechanics. One of the consequences of this Dirac equation was that the electron should have a partner, an antiparticle of the electron, and this was discovered by Carl Anderson in 1932, for which he got the Nobel Prize in 1936. Anderson also, of course, found pair production through high energy photon interacting with silver and lead to produce E plus and E minus. So these are the original references. And this is a picture of that discovery, which is there in the discovery paper of Anderson, where using cosmic interactions in a cloud chamber on which he had superposed a magnetic field, which is perpendicular in this case to the image, or the plane of the image. Then you have a cosmic ray positron that enters this cloud chamber. You can see that because of the magnetic field, its trajectory is bent. But subsequent to energy loss in the lead plate here, which is interposed in between, the curvature increases. So it starts out with a 63 MeV positron, cosmic ray positron, and then ends up with a 23 MeV particle. And of course, the curvature tells us about the charge on this particle. And so this is how the positron was discovered by Anderson. So let me summarize what we have talked about in this lecture. We have discussed the hierarchy of matter in terms of its constituents and the different forms of constituents which come together to form solids, liquids, etc. Then the discovery of the atom, of course, this was done earlier in an earlier lecture. Then the electron, photon, proton, neutron, and the positron. Almost all of these discoveries earned their discoverers the Nobel Prize in Physics. Thank you.